Hello everyone, we are going to start section 2.1, integrating factor. That's going to be a long lecture, so get ready and make sense to do some notes while I'm explaining the section 2.1, integrating factor. This is one of most general ways to solve a linear equation of first order. So I'm going to start with explanation of the method on a simple example and then give you some general ideas. First, let's think. If somebody gives you the derivative of some function equals to 2x, how do you find function? How do we find f of x? Well, we know that we just have to integrate it, right? So we kind of integrate both sides here. I'm going to write it down. The integral of f prime dx is going to be equal to the integral of 2x dx, right? On this side, we do remember that integration, and differentiation, according to the fundamental theorem of calculus, are inverse operations. So we are just going to have f of x over here, or antiderivative. What we have on this side is x squared. Remember about the constant, right? So that's how we solve a primitive differential equation. Derivative equals 2x. Now, let's imagine that my function f of x is a little bit more complicated. Imagine that f of x looks like, why do I call it f of x? X squared multiplied by y of x. Product of two functions, x squared and y of x. Y of x is kind of unknown function. Right now we don't care what is the function. Eventually it's going to make some sense. Let's differentiate this f of x. Let's find f prime. Remember, whenever we differentiate a product, we're supposed to use a product rule. Product rule tells us differentiate the first factor, 2x, multiply by the second factor, y of x. Differentiate the second factor. Why? Because we don't know the function, I'm just going to put y prime of x and multiply by the second factor. I put second factor first, okay? Just like to keep the order. Okay, so that's going to be my f prime. Now, imagine that somebody gives you a differential equation, and differential equation is going to look like this. Somebody gives us differential equation looking like this. First order, supposed to be linear. If we divide by x squared, we are going to get a linear equation, right? I put derivative here just because I was trying to keep the order I have from the derivative. But you kind of compare this, and you see, okay, this one is actually a derivative of the product. You can write down that this conglomeration, or these two terms, equals dx, derivative of x squared, y of x, right? And on this side, you have 4x cubed. Well, what should we do if we have a derivative on one side and a function on another side? How do we find what is antiderivative? Remember the previous example, we just integrate both sides. Integrate this side, integrate this side. If I integrate a derivative, according to fundamental theorem of calculus, I'm going to get the function itself, right? And here I have 4x cubed dx. Well, here, differentiation and integration are kind of canceling each other because they're inverse operations, right? And I'm going to get x squared y of x. Here I just do the integration. What is antiderivative of 4x cubed? Well, it's 4x to the power of 4 over 4 plus a constant, right? Now, because differential equation was about y, we'll need to find y, right? How do we find y from here? Well, we just divide by x squared. Y of x equals x to the power of 4 plus a constant divided by x squared. I'm canceling the 4, okay? And I'm going to get 1 over x oh, not 1, constant over x squared plus x squared. I'm dividing each term by x squared. This one is going to, the last term is going to be constant over x squared, and the first term is x squared over x to the power of 4 over x squared, which is going to give me x squared. Okay, good. Well, basically I solved it. I don't know the constant yet, but eventually if somebody gives me initial conditions, I can find the constant. And I solved this differential equation, right? Not very difficult to solve, but you're supposed to kind of recognize derivative of what is this term, and that's not kind of easy, right? I mean, I differentiated the product to show you that it's going to be a derivative, but if you look at the expression, it's kind of hard to guess, right? Derivative of what is this? Unless you suspect already that's a product rule, and there are supposed to be two functions, right? And you start looking over here. Well, if this is derivative of a second term by the first term, by the first factor, mean that the first factor is x squared and the second factor is y, and you can kind of guess this way. Okay, now imagine that we have slightly more complicated problem. We are still not talking about integrating factor here. Slightly more complicated problem can look like this. Let me write it down separately. What if we have a problem looking like this? Y prime plus 2 over x y equals 4x. You start looking at the problem and you see, okay, imagine that was a product, right? And you differentiated it, but this is just derivative of y. There is no second factor. The derivative of second factor is equal to 1, right? And if you assume that derivative of the second factor is equal to, there is no, second factor is equal to 1, right? It's 1, the second factor by the derivative. And if you compare it to this expression, you understand that if second factor is 1, then derivative of second factor is supposed to be 0, and it's impossible to roll it into a derivative of the product. And you start thinking, okay, but maybe if I multiply it by something like x squared, it can be rolled. How about this? Multiply by x squared. I'm going to write down x squared y prime plus 2 over x y by x squared plus equals 4x by x squared. X squared x. Okay? Just thinking, does it like maybe it's gonna work better? I'm going to write it down in simplified form. X squared y prime. Here I'm going to cancel one of the x's and write down that this is 2x, right, y. And here I'm just going to write down 4x squared, cube, sorry. Now, after multiplication by x squared, I'm going to compare my equation and see, wow, that's exactly the equation I had on the top, and I solved it already. Look, 4x cubed, right? And then x squared y prime, 2xy, 2xy. So exactly same equation. So, of course, solution is going to be same. But initially, it was very hard to kind of guess what two functions are going to make up a product, which is going to be like working here. Well, I gave you a clue that we multiply by x squared, and it's going to work, right? So, but actually, yx squared, why not x cubed, for example, or not sine of x? Actually, this x squared is called integrating factor. This is integrating factor. Why do we call it integrating factor? Well, after multiplication, you can integrate it, right? That's why we call it integrating factor. So it's kind of complementary factor by which you multiply and equation is possible to integrate. Now, is it like we have to guess about it always? Sometimes guessing is very easy. I mean, when you see the equation first time, it's not easy, but you see like 3 equations like this and you already can guess. Just trust me. You do the homework. On equation number 3, you will be able to guess about integrating factor. But do we have any scientific method to find this integrating factor, which is going to turn this equation into something nice like a derivative of a product? And yes, we do have a scientific method, and that's what I'm going to teach you. Okay, so let me, maybe I can start over here. We still have some space over here. So let me write it down, summarize it. We can about x squared or find it. So how do we find it? Well, guys, remember that we are kind of multiplying by this x squared, right? So why don't we assume that it's unknown function we are multiplying? We don't know yet that it's supposed to be x squared. We remember that after we multiply by it, we're supposed to get a derivative, right? This expression is becoming a derivative of 2 integrating factor and y. Let me kind of maybe show you the idea like this. I'm going to write down the equation. Y prime plus 2 over x y equals 4x, and then multiply by integrating factor mu of x on both sides of this equation, mu of x. Well, we already know that it's x squared, but how do we get x squared if nobody gives it to us? So assuming that mu is unknown integrating factor, mu of x is unknown integrating factor. The idea is to find the function which is going to roll into derivative. So here what we have mu of x multiplied by y prime plus mu of x by 2 over x y, right? And we want to roll it into a derivative, dx of some product of 2 factors, right? We know that one factor, according to what we have, all the solutions, is going to be just y, right? Because eventually we're supposed to get y here. You know that one factor is y. If you look at this term and you have a second factor y differentiated, then mu is going to be the first factor. So I'm going to put mu over here. Well, there is no other option, right? If you differentiate mu y, as a second factor y is going to give you y prime, copy the first factor mu. Here is going to be what? This conglomeration is supposed to be equal y multiplied by mu prime. Well, just because I assumed that it's a product, right? Let me write it down one more time. So we have mu prime y plus y prime mu, right? So y prime mu is this one. That means that this one must be mu prime y. Let's write it down. Give me a second, I'll put it in switch and make sure that it fits into my screen. Okay. Let me write down what it's supposed to give me. Mu of x, 2 over x multiplied by y is supposed to be equal mu prime y. Mu prime y. You see y repeats on both sides. We are assuming that y is not equal to 0 because this way is going to give me a trivial solution. So I'm going to cancel it and I'm going to write down that after that we have equation mu of x by 2 over x equals mu prime. How do we solve this equation? Well, we have function of x and we have mu. Mu is not y actually, but we can call it y. And we can separate variables. I'm going to put everything with mu on one side and everything without mu on another side. Remember that mu prime adds d mu dx. So I'm going to put here mu of x. Supposed to move mu of x actually this way. Okay, let me write it down one more time and then do the separation of variables. So I'm moving x over here and I'm moving mu over here. I'm going to get 2 over x dx here, right? And on this side, d mu over mu. Well, just mu goes in denominator and that dx goes in numerator. Well, remember, we started our chapter 2, not with section 2.1, but with section 2.2. Why? Because I wanted you to know separation of variables before we start using it. Otherwise, you won't be able to solve this equation, right? Well, if I integrate both sides of this equation, what I'm going to get? Well, I'm going to get 2 ln's, right? 2 ln of absolute value of x equals ln of absolute value of mu. Well, plus a constant, of course. Don't forget about the constant, right? Let me add it. So I'm going to add it on the variable side like this. Now, what I'm going to do? I'm going to do my standard procedure. Put exponential function into the power of this side and exponential function into the power of this side. I'm sorry that I'm not copying it again. I'm just doing several operations on the same line, but it's going to be a long lecture and I'm trying to make it shorter. So remember what happens when you put e to the power of c. It's just going to give you a positive constant. What do we have here? We have e to the power of 2 ln of x. I'm not going to touch this yet. I'm going to just deal with this part. E to ln is supposed to cancel each other, cancellation equation. They're inverse functions. And I'm going to get absolute value of mu. What should I do over here, guys? To modify this side, let me copy absolute value of mu, my right side. I'm going to write it down like this. E to the power of ln of absolute value of x. Remember that when we multiply 2 powers, we are kind of raising power into a power. Actually, if you have like power of a here and power of b here, you multiply them and get expression a multiplied by b if you raise power into a power. By cancellation rule again, I know that e to the power of ln is going to give me just x, right? In our case, it's going to be absolute value of x squared. Well, fortunately, absolute value of x or not absolute value of x, anything squared is going to be positive. So I'm just going to write down c x squared. And that's going to be my absolute value of mu. So actually, actual mu can be equal plus minus c x squared. Or if we allow c to be positive and negative, it just can be just c x squared if c is positive or negative. Here, this c is strictly positive, right? Because it's e to the power of c. So, what is next? Did we get our integrating factor? Almost. We have mu equals cx squared. Actually, there is not only one integrating factor for this equation. There are millions of them, right? Depending on the constant, you can have 2x squared, 3x squared, 5x squared minus 4x squared. Well, you don't need all of them, right? You actually need just one integrating factor. Let me move this page over here. You just need one, still not visible. We just need one integrating factor. And in our case, it's x squared. So we can set up c equals 0. We just need 1 mu of x. So use c equals 1. Can you use c equals 2? Yes, guys. You can use any c, actually. Your answer is not going to be different because you are using a different integrating factor. Because integrating factor is just like auxiliary thing over here. It helps and it leaves. It's not going to leave a trace of itself in our equation. So that's up to you. Okay, so we see how it looks, right? And that's our integrating factor. What conclusion can we draw from this solution? Like what we actually did. We multiplied both sides of the equation by some unknown function, and we found this unknown function by kind of assuming that the second part of the product rule must be equal to the second part of the product rule, right? I can do it a little bit more general and give you the formula for integrating factor. Let me show you the previous page. Unfortunately, it's not the board. I cannot show you 2 pages at the same time. Let me show you the previous page. Remember, when we multiplied by integrating factor over here, we got actually the one term of the product rule and the second term of the product rule. equation was given us by the second term of the product rule, and we were comparing it to just the product rule of y multiplied by integrating factor. Well, that can give us general equation for finding integrating factor. You just kind of compare this side to, let me double line it over here, double line. So the second part is giving us actually equation, right? If you look at this equation, you see that y is going to be same here and here, right? So actually that's a coefficient of y. That's a coefficient of y, which is going to eventually appear on this side, right? And mu prime on this side, and mu multiplied by this coefficient. So general equation, well, I want to, before I move to very general form, I want to solve one more problem actually. I don't want to give you general equation for finding mu. So let's solve one more example, and then I'm going to give you a general formula, okay? Because I don't think the general formula is useful right now. Did we get our solution? Well, we got it a long time before, right? When we were solving equation, and solution was actually c over x squared plus x squared. And there is no trace of integrating factor in it, but you see it's somehow similar to integrating factor. Let's try another example, and then I'll give you a general approach to find the integrating factor. Example 1, let's call it example 1. That was kind of our lecture, but example 1. So example 1 is going to help us to solve y prime plus 2 over x y cosine of x over x squared. Okay, you guys probably recognize that the right side of this equation is exactly the same to what we were solving. So integrating factor here is x squared. I'm going to give initial conditions here. And we are searching solution for x greater than 0. Okay? Well, we can repeat the process of finding integrating factor here. But because we get the very same equation, let me show you the previous page. That's a very same equation on the left side. That's y prime plus 2 over xy, which we have over here. We're going to get the same integrating factor, no matter like we do it using mu, or we just guess about it. But it's going to be same, right? Even if we use mu or do not use mu. So here we were using mu and got integrating factor, like integrating factor was, let me write it down, mu was equal x squared, but we can just use it here. And that's what I'm going to do. I'm going to show you like what to do after you found integrating factor, because integrating factor is just half of the solution, right? We did some auxiliary step and we still need to solve equation. So let's kind of see how do we finish equation after you find integrating factor. So integrating factor is x squared. I'm going to write it down mu of x, but not necessary, right? So I multiply my equation by x squared. That's x squared y prime plus 2 over x squared y equals cosine of x over x squared by x squared. Lots of people forget to multiply integrating factor by the right side, and it's making their life very, very difficult. Okay, here I know that that's x squared y prime plus 2xy, right? This side x squared cancels, we get just cosine of x. And here we already see that what was differentiated was x squared y. If you differentiate y, you're going to get y prime multiplied by x squared, and then you differentiate x squared, you get 2x multiplied by y. So the derivative equals to cosine of x. So now you anti-differentiate, so you take integral of both sides. Dx. Here we kind of cancel derivative and antiderivative, and here we just integrate the cosine, which are going to give us sine of x plus a constant, right? And solving for y, we are going to have sine of x over x squared plus constant over x squared. That's going to be our solution. So if you know integrating factor, usually that's just a matter of finding the right side integral. If you can find it easy, in this case it was super easy, right? Derivative of sine is cosine, so kind of. Last step we'll need to do is to use initial condition y of pi equals 0. So I'm going to plug in y of pi. I know that sine of pi is equal to 0, right? That's a c of, pi square. And that's supposed to be equal to 0, right? Well, looks like this 0. So this is 0, so there is no escape for a constant to be anything else but 0. So my solution here is y equals sine of x over x squared. And they're asking us only for positive solutions. We are fine. We're not going to have any problems with denominator equals to 0 because x is always greater than 0, right? Otherwise, everything looks fine, right? Unless we did any mistake. Let me check everything for little tiny mistakes. Well, it doesn't look like we miss any minuses here. 0. Yeah, the sine of, let me double check. Is it pi? Yeah, that's pi. Sine of pi. Remember that sine of 0 and sine of pi are zeros, right? So that's final solution. And there is no integrating factor in our final solution. I mean, you do see integrating factor actually here hiding, right? Okay, now we are ready to do some general theory. A little bit more general, okay? Let me move this one. General theory is not complicated if you understand where you go. So, general theory. Well, for general theory, we'll need to consider general equation. What kind of equations we are solving here in general? In general, guys, our equation is going to look like this. Y prime plus p of ty, it can be p of x, y, equals g of t. So, general equation. So, normal equation is going to have two terms on the left side, one term on the right side, can be two terms. Actually, g of t can cover as many terms as we wish. But here, usually you have two terms, just because the product rule usually gives you two terms, right? And let's assume multiplication by integrating factor. So we multiply the whole equation by integrating factor. So we have mu y prime plus mu p of t y equals g of t mu, right? We want these two terms be actually d dt of a product, right? Which product? This one, right? Mu y. Why? Why we want these two terms to be equal mu y? Well, if this is a derivative, then this is a function. So the function, and this is a second term. So if you have these two terms, we are going to get this as a one of the steps of product rule. We just differentiate y multiplied by the second term mu. We do know that if you differentiate actually this expression, we get mu y prime plus mu prime y, right? If this term is equal to this, if these two terms are equal, then this term must be equal to this, which is going to give us equation on mu. Let me write it down. Mu p of t y equals mu prime y, right? Well, we're going to get rid of y, and we are going to have mu p of t, mu of t too, but just like, and here d mu dt, from where we can have d mu over mu. Again, I'm taking this mu, moving it here, and I'm taking this dt and moving it here, equals p of t dt, right? Well, in general, I don't know what is going to be the function p of t, so I'm not going to really give you the formula here. I'm just going to integrate this side. If we integrate both sides of this equation, we are going to have ln of absolute value of mu equals, well, here I'm just going to keep it as integral, okay? P of t dt. Well, now I really don't care, like there are going to be many solutions for mu, but I just need only one. So I'm going to use positive mu. Actually, when you have absolute value, means that negative mu is going to lose a sign. I'm going to use only positive mu. So I'm going to have ln of positive mu equals integral p of t dt. And then I'm going to raise it to exponential power, cancel this e and ln and get just mu. And here I'm going to have e to the power of p of t dt. And if I know what is integral, I'm just going to put the result here. But right now I don't know, the function is unknown actually what I have, what function, what coefficient I have. So I'm going to put it in general. Okay, so basically I found integrating factor, and this is general formula for integrating factor, right? Usually we are going to set up a constant which comes with this integral to 0, right? We don't need lots of integrating factors, we just need one integrating factor. So if you calculate the integral, it's going to give you a constant right here. We set it up to 0. We don't need a constant actually. Or you can set it up to anything actually. Remember that it's not going to affect your solution. My suggestion, for example, once, do not set it to 0 or set it to some other number and calculate what you are going to get as a solution of differential equation with a different number. You see that it's not going to affect the solution. We are trying to make a simplest integrating factor, but you can make it a little bit more complicated, still gonna get your solution. After you found the integrating factor, what are you going to have? This equation is rolling into derivative, back to equation. Back to differential equation. So my differential equation is going to roll into a derivative, right? I have d dt mu y on this side and g of t mu. I already know my mu, that's integral, but well, still gonna be known if I know p, right? So I integrate both sides, dt mu y equals integral of g of t mu of t dt. Here they cancel and I get mu y product. Here integral g of t mu of t dt. And now I can calculate y by dividing this by mu. So I'm bringing this mu in denominator here. And I don't know, guys, if you kind of like long formulas. But so what is actually mu? Remember, mu is e to the power of p of t dt. Well, to me it looks like I have too many t's here, right? I have t here in this integral and t in this integral. And when I do the integral, eventually I'll need to have a function of t as well. So what I'm going to do, guys, I'm going to change my variable a little bit. But that's just for the formula. I'm going to write down mu. Well, still, mu is this one. I'm just don't want to copy it in denominator. And I'm going to write down here g of s e to the power of p of s ds. Well, it's probably s is not a good idea actually. U maybe. U from s0 to s, and here from t0 to t ds. Wow. Well, that's not supposed to be actually just s. That's a general formula. I would not suggest you to memorize this general formula. If you understand the idea of integrating factors, that we need to roll two terms into the product. And first term is going to be the product of integrating factor and derivative. Then the second term is derivative of integrating factor by the function. So we kind of get equation on a derivative. I think that's all you need to know. So, but what is interesting, if somebody gives us equation like this, we don't have any conditions on these coefficients, any special conditions, except maybe that this function is integrable and this function is integrable, right? And we can get a general solution. And integrals are giving us unique solutions. So we are answering first two questions I was asking in first lecture. Does solution exist and is it unique? And actually for equation like this, solution exists and it's unique and it's given by this formula. Well, we're not going to use the formula, but I know some people like to memorize formulas. You can always use the formula, though I would not recommend you to do this. Okay. Well, I think we are going to talk about uniqueness theorem in the next lecture. I don't want to mix it up with this one. Okay, well, I want to consider one more example, because so far, guys, we had just one integrating factor, and it was x squared. But let's consider another example and maybe have a different integrating factor, which is not x squared, but something else. Okay, so example 2. I'm going to give you an equation to solve, and maybe, guys, you can try to solve it for a while on your own, and then I'm going to help you to solve it. I think that's going to be a good idea. So y prime plus 2y equals t e to the power of negative 2t. And I'm asking specifically, find the integrating factor and solve differential equation. Here I don't give you any initial conditions, so you just solve it in general. I'm going to count to 3 and then solve it myself, but at this point you can stop your video and try to do it yourself. I'm counting 1, 2, 3, and I'll start solving it. Well, I'm not going to use my formula, I'm just going to multiply it by integrating factor. So mu y prime plus mu, continuing, mu y prime plus mu 2y equals mu t e to the power of negative 2t. So I multiplied everything by integrating factor mu, which I'm going to find. I'm going to compare it to mu y derivative. So mu y derivative plus mu derivative y, right? So I do have mu y derivative here. So this one is supposed to be mu derivative y. Y and y are same. So I'm going to write down then 2 mu. This one is equal to mu prime. From where I'm going to write down 2 mu equals d mu dt. From where, putting t here and mu here, I'm going to find that dt 2 equals d mu over mu. So ln of mu. What is integral of 2? Well, integral of 2 is 2t, right? And I think plus a constant. Well, I'm going to raise e to the power of both sides and get mu. And again, I'm going to assume that mu is positive. So I don't need actually consider plus minus. And e to the power of constant, e to the power of constant is going to be my new constant, so it's c e to the power of 2t. I'm going to set c equals to 1 because I need just one. Need just one mu. Okay, so my integrating factor actually is e to the power of 2t. Integrating factor. Now I'm just going to use it. I already know that my right side multiplied by my left side, sorry, multiplied by integrating factor, it's a derivative of mu and y. So I'm going to write down e to the power of 2t by y derivative, and on the inside I'm just going to kind of put actual integrating factor e to the power of 2t t e to the power of negative 2t. Oh, well, very nice match, right? These two are going to cancel and give me just t. Now I'm integrating both sides, integral of e to the power of 2ty derivative dt and integral of t dt. Well, what can be easy here, derivative and integral are cancelling, e to the power of 2ty, and here I have t squared over 2 plus a constant. Dividing by integrating factor, I'm going to get t squared over 2 plus a constant divided over e to the power of 2t. Well, if somebody gives me initial conditions, I'm going to plug them in and calculate c. Otherwise, I don't think that we can simplify it further. Well, you can multiply by 2 and put 2 in denominator. And remember that 2 constants is still a constant. Otherwise, I think that's a final answer. Okay? Okay, So I think that's going to be all for this lecture. I think it was enough to digest for the first time. Okay, thank you.